Hi, my name's Akila Boina, and I'm going to be talking about derivatives and rates of change, which is section 2.7 in your book. Derivatives and rates of change have many different similarities between different topics, such as the tangent line to a curve, instantaneous rate of change, and velocity all have the same type of limit, which is called a derivative, and that's what we're going to talk about. So let's go over the basics. The average rate of change is the same thing that you know as a slope. So if you take point P, and take a point close to it, which is Q, and you find the slope of the secant line, that would equal the change of their y, which is f of x minus f of a, over the change in their x coordinate, which is x minus a. And that gives you this slope, written by this formula right here, m of pq. Now, if you want to take it a step further and find the slope of this line at just point P, what you'd have to do is let Q approach P by letting the x-coordinate of Q, which is x, approach the x-coordinate of P, which is a. And that would give you m of PQ, the slope of PQ, the secant line, approaching the number m, which would be the slope of the line that would cross just P. This is also called a tangent line, which is basically the instantaneous rate of change at that one point P. You can find that by the limit of the difference in the y coordinates over the difference in the x coordinates as x approaches a. X is approaching a here when you're making Q approach point P. Another formula you can use that would make it easier in some problems is if you set h equal to x minus a, which is the interval of the change of x, then x would equal a plus h. The secant line PQ's slope would be given by MPQ equals f of a plus h minus f of a over h. As you can see here, that's the y difference and that's the x difference. So the limit of f of a plus h minus f of a over h would give you the slope for that tangent line. H is approaching 0, if you remember, because h is x minus a, and x minus a would have to be getting closer and closer to 0 so that you can have this tangent line, where q and p are equal. So we can talk about velocity because velocity has the same type of limit as the tangent line and the instantaneous rate of change. Considering s of t, which is a position function, which is displacement s of an object from the original time t, you can see here by this diagram, that's the change in y, and t which equals a, and t which equals a of h at this point is a change of x. So you can get your average velocity, which is the same as the slope of the secant line, by displacement over time, which is the change in y over the change in x. And h is the change in x because h is x minus a. So if you compute this over shorter and shorter time intervals, you would get the instantaneous velocity, which is given by this, which is the same as your formula for the tangent line. Because this limit is used over and over and is very useful, and is also used in so many different studies and fields of science, they're given a special name and notation. The name is derivatives, and the notation is f prime of a. The derivative of a function f at a number a, denoted by f prime of a, is f prime of a equals limit f of a plus h minus f of a over h as h approaches 0. Another way you can write this is like this, which is the first way you learn to write a tangent line. So you can write it in either way, as you've seen in the other slides also. So we're going to do an example problem. Find the derivative of the function f of x equals x squared minus 8x plus 9 at number a. So you have your derivative formula, the limit, and so you can put a of h in place of x for the first, that part. So you just square it and then multiply by negative 8 plus 9. And then you put a as your x here for this. Then you'll expand this by distributing each of the things you need to and simplify it by crossing out. So you get 2ah plus h squared minus 8h. And that would give you this if you cross out the h's. And then finally you get 2a minus 8 as your derivative. And you can think of the derivative as the same as a slope. To take that problem a little bit further, find an equation of the tangent line to the parabola at the point 3, negative 6. So you have your derivative and the slope of the tangent line at 3, negative 6. You just have to plug in the x coordinate, which would be for a, and you get negative 2. That's your slope. Use the point slope formula and use your coordinates, and you get the equation y equals negative 2x for your tangent line. The end. Thank you. I hope you learned something from this video.